Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video.
In the last number of video tutorials, we focused on the open buildings data set in particular, but in general, we looked at the human footprint, where there are human settlements, for example, or urban structures, or urbanization, etc., etc. So we particularly looked at our region of interest, identifying locations within our region of interest of human footprint, or more specifically, built-up structures. And as I said, we looked at a number of data sets, but we focused predominantly on the open buildings. And I gave in those video tutorials a number of reasons why I particularly enjoy working with the open buildings data set. And then obviously, there's a lot more that you can do than just downloading there's a building, here's a building, or there's a build-up structure. We actually worked on creating, generating the size of each of those structures, and then the height of each structure, etc., etc. So I think it was quite a useful exercise, and yeah, I thoroughly enjoyed it. But that said, we're going to focus now at a new topic, and that is the dynamic world data set, which I think is also very, very interesting data set to work with. So the next couple of video tutorials, that will be our main focus. Not to say that we won't get back to the open buildings, but for now we're going to park that and continue with our journey, and that's taking us to dynamic world. Now, let's quickly just go to the dynamics. As I said, I go to my Google Earth engine, I go to data sets, and I type in dynamic world. Okay, so let's quickly go there. We go dynamic world, and we press the run button, and there we go, version 1. Okay, let's quickly go to the website. Okay, so there is the data set, the landing page or the website of Dynamic World. Okay, it is available from 2015 to 2024, so that gives you about 8 years of data, but you can create an image for each and every single Sentinel image within that 8 years. Okay, so if there's 4 or 5 images in a particular year, you can do you can run it for each of those images, so it's not per year necessarily. Okay, so it's the provider is the World Resource Institute. There is the unique identifier, but underlying this particular image or this data set is the Sentinel-2 level 1C images, daytime images. You see, it's exactly the same time period as the dynamic world. Okay, so the dynamic world data set is derived or is built upon this daytime image, or the Sentinel-2 level 1C daytime images, but we'll get to that. Okay, so it's World Resources. There is a description of it. As I said, it is built on the Sentinel-2 image. There it says it's built on the Sentinel-2 image. You can go through there's a tutorial series on it, etc. And obviously there's the startup code for it. Anyway, so we're going to work with Dynamic World version 1. Now, there's a number of things that we're going to do with this, not just what is available within this landing page. Just remember, the Dynamic World data set is derived or is extension of the Sentinel-2 MSI level 1C data set. Okay, and that data set is a normal Sentinel daytime images with bands from B1 till B14 or whatever the case might be. Okay, so just remember these two are interconnected. You cannot do dynamic world without the Sentinel. The Sentinel is leading to dynamic world. Okay, there's two other sources of information which I would recommend when working with dynamic world data set. and that is within the Good Earth Engine tutorial within the community. There's a tutorial 1, 2, and 3 that goes into great details on the data set itself, and I would recommend a bit of time studying or working through this, or opening it at the same time as you work in the Earth Engine itself with the code. And then there's this particular site that gives you a nice exercises on working with Dynamic World. So these two source websites, I think, is of great use and of great value when you work with the data set. Now, what we ultimately, well, not, it's the only thing, but something that we can do is creating a image like this for your region of interest. So this ultimately is one of the outcomes or outputs of the dynamic world. There's many others that we're going to do, but this is one of this. So creating image like this is what is referred to as dynamic world. Okay, this is sort of a 3D image of your region of interest. Okay, so I hope that makes sense. And as I said, there's a number of video tutorials where we're going to work with, but for now, this is what we're going to create. We're going to create an image like this or a layer like this for your region of interest. Okay, so let's get going. Okay, so first of all, always I load my region of interest, and there is 4 regions of interest located. Now, just bear in mind that there are size constraints, so you won't be able to do an image like this for a very, very large region of interest, like for a whole country or a whole, let's call it in our case, a province. Okay, so at best you would be doing it around a city level or size level of towns or a big city, but you won't be able to do an image like this for an extended region of interest. So just bear that in mind, that there is size limitations to what you can do here. So if you want to do an extended period, extended location, most probably will have to do it in 3 or 4 images and then export them to your GIS program, and from there merge those images into the bigger your region of interest. So just a note of caution here. Okay, now let's go on with it. Let's open our regions of interest. I've loaded them as per normal. I use my asset here, and I just new and import it as a shapefile. Okay, so obviously that's where all these assets come from. Okay, then obviously first step always, I display my region of interest using that particular script. In this case, I'm going to focus on table 3, which is Veldrift. Okay, this town is called Veldrift. Okay, I'm going to activate my satellite in the meantime. So this is a town where I stay, in my specific location called town called Veldrift. So that's what I'm going to display, and I'm going to center my images or my maps around my region of interest, and this is obviously my zoom level, and then my clipping function. So these first 6 lines of code or script are standard practice for me. I copy and paste it before I start with anything. I copy and paste it, and I load my regions of interest. So that should be something you do without even thinking about it, so to speak. As I said, then I'll just make references to that 2 source documents, which is this one here, the community tutorials within the Earth Engine. Okay, and then obviously this particular one of Gandhi, where it goes into the great detail about the ins and outs of Dynamic World. So there's my 2 source documents that I'm working with. Okay, so first thing is to say is the time period that I'm working with. Okay, remember it's starting from 2015 and then it goes all the way to 2023, so 8 years, but multiple images per year. So the number of images total images you can create is, I don't know exactly the number, but it's number of images per year, which is generally about 2 images a month. So let's say that's 24 images a year, and then obviously the 8 years, whatever that number is. You can do the calculations. Right. So we specify a start date and an end date, and that is because we need to identify a image. So we cannot work with a composite or a median image like what we've done previously. We have to work with one particular image. So not knowing the exact number or date of the images within a particular period, we basically specify, in general specify a year, and then I'm telling for this code, in this sentence there, find the first image in that particular period. Anyway, so I specify a long enough period, so I know within that period there's definitely going to be an image. And then I specify within the code, within this period, give me the first image. Now, you can most probably say the last or something to that effect, but first image should be fine. Okay, so if you want to do a shorter period there, let's say you only look at it at 1 month, the chances you're going to find an image within this month is most probably very little. Well, you won't find it because the data set, if I go back to the source, the data set only starts at 6 months. So you're not going to find an image there. So I need to actually make that 6 and make that 12. Okay, anyway. So that's where you start the date. Make the period long enough so that you're sure you're going to find an image. Then I'm telling you I want to work with the Sentinel. Find the Sentinel image within this. I'm going to work with Sentinel. Find all the images in this range. This is what this code. Well, first of all, I clip it. Same here. I can leave it there, or I just for standard I clip it using both sets of codes. Okay, so I filter it for this whole period, and then importantly, it's for a cloud cover of less than 35%. If you go into the tutorials, it will tell you that it cannot work with must be less than 35%. It has to work with a cloud cover of less than 35%. Otherwise, it's not going to be able to generate the classification. So maximum value you can enter there is 35. Now, always try to work with as smallest value as possible, but understanding there may not be images. So yeah, it's a tricky one here, but work with it. So here I'm just specifying my date. I'm specifying the data set. I'm specifying my region of interest and the cloud cover. Okay, so this is what I do here. As I said, what I'm doing in this particular piece of code is I'm saying within that time frame, within that specified time frame, find me the first image. I want to work with the first image. Okay, and then the color scheme or the visualization parameters of that image. Remember, it's a true color, which is B4, B3, and B2, which is red, green, and blue. Okay, so that's my true color, and then I'm going to display the image. Okay, then I'm going to display the image. So this is still fairly standard script. There's nothing strange about that. Maybe just, get me the first. And as I said, you can don't generate a median image, mean image, meaning getting a composite for this whole period. Find an exact image, because it doesn't want to work with derived values. You want to work with the specific values of a image. Okay, so find the first image. Okay, then what we're doing there is to say, okay, now once we know the image, that the Sentinel image that we're going to work with, that image will have an ID number. Okay, that is, that's what it says. It's going to have an ID. That is the system index. So now it finds us the ID number of this particular image. Okay, so remember that would be So let's go to this. So we're going to print the image, the ID number of the first image, and this is what this is. Okay, so this is the ID number of the first image in this first Sentinel image in this range. That is what we're generating there is that ID number. Okay. And why do we want to generate that ID number? Because that ID number must now be aligned to the image within the dynamic world. Okay, so remember, we want to work with a dynamic world image, but it's built upon, or it's derived from the Sentinel image. So we're going into our time period. Okay, find me a Sentinel image, or find, in our case, the first Sentinel image for my region of interest within that time period. And then once you've identified that Sentinel image of my region of interest within that time period, get the ID number of that image. Let's say the ID number is X7 or B12, whatever. Well, there's the number in. Then now we've identified that number. Now go to the Dynamic World Dataset and find me the corresponding Dynamic World image that relates to that specific first Sentinel image in my time frame. I hope that makes sense. Because now you're saying, go then to my Dynamic World and filter that image collection. Remember, there's a lot of images there. Okay, filter that image collection and match. Okay, it's like, you know, a match in or lookup table in Excel. There we've identified the ID number. Now go to this and find the ID number in this data set that matches that first image, first Sentinel image in that time period. And this is what we're doing here. Okay, and then we're gonna obviously generate its ID number, and you'll see there's the ID number. So there's the ID number that corresponds in the okay, so there's the bands. Okay, so I'm going to go to that now. Yeah, so there's the system index number there. You'll see that that number there corresponds to this number there, and then we match it, so it's now a match. Okay, so now we've got the Sentinel image, Sentinel dataset image for my region of interest for my period, and it's matched with the Dynamic World image. So I'm working with it similar to images. Okay, so that's basically what we're doing up to here. Okay, I hope that makes sense. Then we generate a visualization parameter. Now within this data set, within the Dynamic World data set, there's bands. Okay, so let's go into the dynamic dot. Let's go to the bands. Okay, so what and the other nice thing, it's 10 meters resolution, so it's very, very good. It's very, very good. Okay, so what is our bands? Okay, we have 9, I think, which is water, trees, grass, flooded vegetation, crops, shrubs, built-up area, bare soil, snow and ice. Yeah, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, there's 9 classifications, land cover classifications. Okay, remember this is ultimately a land cover classification data set. Okay, so I should have said that from the beginning. And it classifies land cover by these 9 categories or classes, which is called bands: water, trees, flooded vegetation, crops, etc. Now, what the Dynamic World does is it allocates a probability to each of these classes for a particular location. So let's say you have a particular location within your region of interest, then it will now estimate the probability of each of those classes for that specific location. So it identifies a location and it will say, what is the probability that there's water? Or what's the probability that there is bare soil? Or what's the probability that it's built up? Or what's the probability that there's crops? Okay, so it won't tell you with 100% confidence that is water. It will say there's a 90% chance that there's water. And then obviously the other 10% will be those other classes. Okay. So it gives you a probability distribution for each of those classes for your particular location within your region of interest. And we're going to get through that. Okay. So importantly, it's not an absolute number, it's a probability number. It's a percentage, and for each location we'll have all these classes or categories, and that will add up to 100%. Now obviously there would be one particular class that's dominant and the others would be secondary classes, but it does give you a probability distribution for each based on all these classes for your region of interest. Okay, so that is, if we go to here, this is what the bands are. Okay, so the bands are water, trees, grass, flooded, crops, shrubs, built up, bare soil, snow, and ice. Okay, so there's your 9 classes. And I said that must be 100%. And yeah, so there's the 9 classes, 0 to 8, 0 to 8. And they give you a particular color scheme for those classes. Okay, so to find out what that is, remember 0 is water. Remember 0 is water. So let's copy that particular, come on, paste it back in. Cut, copy. So I want to copy that. Remember, I go to any of these ones. Let's go to my, so let's say my polygon. And I'll press on this nut here, and I paste that color scheme in, and that's blue. So this color scheme is this little blue color, and you can change it if you want to. So that's blue. So water would be blue. Let's go to trees. Okay, trees would be, let's go back to our nut there. Let's go press that color in. Trees is this sort of grayish green color. Okay. Let's have a look and see within our, if they give you the color scheme. Yes, there's a color scheme. Okay, so water is this blue, we've showed it. Trees are that little grayish green color. This is grass, flooded vegetation, crops, shrubs, built up, bare and snow and ice. So there's the color schemes. Now, you're welcome to change it. You don't have to stick with those color schemes. You can change it. So there's my visualization of my land use cover, land cover. There they are. Okay, so I hope you're still okay with where we are now. And then obviously we're going to add this classification to our map. And then, okay, so that is the first part. We are now generating a land cover image for our region of interest, for our specific period, based on the Sentinel image and derived from the dynamic world image. Okay, so rather than us actually going and do the classification, we use dynamic world. Dynamic world generates the classification, supervised classification for our region of interest based on the Sentinel image. So this is basically what we're doing now. And there's only 9 classes or 9 categories, which is these ones as we selected, and that's the color scheme for them. And then we add them. Okay, so let's quickly, up to there, just quickly go and have a look and see what we've done so far. Okay, so there's my region of interest that I've mapped. Okay, there's the Sentinel image. Remember, this is now, we go back here. That is now the first image in our slot here. And that image is on the 8th month. You see, there's the code or the ID of that image. It's 2015, the 10th of the 8th month. So that's August, the 10th of August 2015. So that's the first image. Okay. You'll see there, it's the 8th image. Now there may be in the 9th month, 10th month, 11th month, 12th month images as well. But we've specifically said, give me the first image in this data set. So you can refine it now. You know you can work with that. So you can actually just make it the 8th and make that also just 8th. Now you know, and we can make that, we said it's a 10th. So we can basically, let's leave it the 1st and let's make it the 12th. So we can make that, let's say the 9th. And it will generate, you don't even have to do the first one. You know it already. That's beside the point. Okay. So let's have a look again. And there's our Sentinel image. Remember, this is now the Sentinel image as on 10 August 2015. And it's not a composite, meaning a median image of the year. It's a singular image. There's the classification. Okay, classification as per dynamic world. Remember, dynamic world is the underlying algorithm that calculates these things based on Sentinel. And remember, we have to do the matching of the IDs. Otherwise, the classification won't match the Sentinel image. Okay, so there's the classification. So in general, that is what we've done with supervised classification. Okay, so we've done just supervised classification, but using dynamic world, the underlying algorithm. Okay, but now what we want to do is we want to generate this, meaning it's like almost like a 3D map. It's almost like a 3D map. Remember, these are probability distributions. Okay, these are probability distributions. They're not a singular image or a singular band. They are a population, a probability distribution based on, here we go, based on all these classes of land cover. Okay, so what we're going to do now is to almost generate a 3D where the height of these images, or this land cover height, is equal to the probability of that category. So if the category, if let's say the highest probability of a particular location is 80%, then that would be the height of the land cover, if you understand. So we're creating a 3D, a three-dimensional image where the height, okay, is equal to the probability distribution, or the highest probability category of land cover. That's basically, and that's the difference between these two. You can see the land cover is exactly the same. There's no difference between the two. But the latter image, this one here, is a probability distribution, i.e. a 3D image from this. So this is a 2D image, which is this width and length. And then we generate this image, which is a 3D image, and the height is the probability distribution. Okay, so you will see it now. Okay, so this is what we've done up to now with this piece of code, with this script. I said, now what we now need to do is create the probability distributions. Okay, so how are we doing this now? Okay, so remember, there's our bands, probability bands, which is these classes as they are displayed in Dynamic World. Okay, and what we're going to do is, okay, so you can go for all of these ones, but this is just converting these values into an integer. So that's basically what we're just doing there. Okay, you can see there. Those are probability bands, which is just the probability distribution of each of these categories of classes of land cover. This is what we're doing there. And then basically we're just converting each value into an integer. Okay, these probability values into an integer. So that's basically what we're doing with these two pieces of code. Now, here's where the fun starts. This is where we're creating the 3D. We're doing a hillside. Okay, now hillside is an elevation. Okay, so we're generating, so we're saying, okay, we're going to use the hillside methodology, and rather than using elevation as per digital terrain model or digital surface model, we're using the probability distribution for the slope or for the elevation. Okay, so this is basically what we're doing here. And you'll see within the tutorials, if we go back to the tutorial, you'll see if we go down, the tutorial itself, you'll see here we colorize the hillside by multiplying the classification image with the hillside. Now the classification image is a probability distribution, and that's why we're dividing it by the 255, etc. And you can read all the ins and outs below, because the hillside is a value from from 0 to 255. Now you can't have a 255 probability distribution. Your probability distribution must add up to 100%. So each of those categories will have a probability, and you sum those probabilities, it must be 100%, meaning the lowest probability can be 1, the highest probability can be, the lowest probability can be 0, highest probability will be 1. So therefore, we have to convert this 255 to a value that ranges between 0 and 1. And therefore, we divide by 255. And that's just to convert the hillside, the elevation, to probabilities, which is then 0 to 1. And that's what we're doing here. Okay, we're taking the hillside. Remember, hillside is a elevation parameter based on your digital terrain model or your digital surface model or elevation model, as we did with the open buildings. Okay, so we're using that, but rather than using that in meters of height above sea level, we're saying let's convert this into probability distribution that will be between 0% and 100%. And this is what we're doing here. We colorize it, okay, and then we add that image. Okay, so we're taking basically, let me just do, sorry, we need to exit here, and let's just, sorry, I need to delete that geometry that we've just done to generate, to find out the color schemes. So that's basically what we're doing here. So here's a two-dimensional image, a land cover image, which is supervised classification. And we're saying we want to make it a little bit more spicy, make it more interesting, more visually appealing, etc., etc. You can stick with this if you find it. But let's jazz it up, for lack of a better word. Let's make it a bit more visually appealing. Let's create a 3D image of this. And how we're doing this, we're generating, because, you know, this is not a flat piece of earth. This is, you know, the surface of the of earth is not flat. So let's use the hillside methodology, but rather than use the hillside elevation as meters, we convert that into a probability distribution based on the probability of those categories being the dominant category of that location. And that's what we're doing here. So essentially these two images are exactly the same, but we're just moving from a 2D image to a 3D image using hillside and converting the hillside into probability. Okay. And that's what layer 4 is all about. Layer 4 is the probability distribution, and then we're just visualizing it in this particular color scheme. Okay, you can see there is the blue, which is rivers. What did we said? This red is, let's have a look and see what that red is. That red is urban. Okay, so that red is urban. That is rivers or water. What is this brown color? Let's have a look and see what this brown color. This is the brown color. This is crops. So that's crops. That green is most probably, let's have a look. That green is either trees or, yeah, most probably trees. Not, yeah, this is grass. That is trees. That is bare soil, etc., etc. So pretty much what we've done when we looked at supervised classification, we did it ourselves in Google Earth. Now we're using Dynamic World to generate the supervised classification based on the Sentinel and given the time period that we've put forward and our region of interest and the Z in the two-dimensional. So if I just, let's say, underlead those ones, and we see there's the underlying Sentinel image, and there's the land cover based on the probability distribution. And the height of each of these locations are the probability distribution. Okay, so where there's more equal distribution, obviously it's 100 divided by 8, you'll have a lower, or the elevation will be less. If you have a dominant one, let's say 90, the elevation will be more. Remember, the elevation is the probability distribution. So let's have a look at it. So let's go into that particular, let's just minimize it quickly. Let's go to the inspector and click on, let's say, water, or on this blue. Let's have a look at it. There it gives you the Sentinel, the spectral signatures of each band. Okay, and there we go. There's your distribution. Water, 74% distribution. Trees, 0.03. Grass, 0.03. Flooded vegetation, 0.04. You can see all of these rest, the bare soil, built up shrubs, they're all basically 0.03 or 3%. But the dominant one is water. So it's fairly, yeah, so that's the probability distribution for that specific location. Okay, now, as I said, 73, it's very high in terms of its dominance, so it most probably will be a high elevation, a high height, for lack of a better word, snow and ice, etc. Okay, and then we basically display it using our standard true colors, red, green, and blue. 4, band 4, band 3, and band 2. Okay, and you'll see water is much more visible in the blue spectrum, and that makes sense. Water looks blue and green to a large degree. Okay, So that's why that's the dominant band colors, because water reflects blue and green. It absorbs a lot of red, etc. etc. That's why red is small. Okay. So let's have a look at build up. Okay, so let's click on that specific location. Let's have a look at its spectral signature. There's its spectral, so you can see there. Let's look and see 0.3, and there is build up 0.74. So you can see the probability distributions are very similar in terms of the dominant feature and the secondary features. You can see there red is now the dominant band because it reflects a lot of red color, but it absorbs quite a lot of green and blue. It absorbs a lot, but it is. Let's have a look at, let's have a look, which one shall we go? Bear swell. So that's bear swell. Okay, so let's click on, let's have a look and see. There's bear swell. There we go. That's bear swell. Let's have a look and see what that. There is the spectral signature for different bands. You can see there's bear swell. You can see bear swell is dominant, but you can see there's also a high probability of it being shrubs and scrubs, 17%. So its height would be lower because it's a much more equal distribution. Let's have a look at its, you can see between the three bands, it's again quite a lot of red, but also quite a lot of green and blue reflectance. So it's much more equal. So its height elevation will be less. There is trees. Let's have a look at the trees. You can see that is trees, 36%, but it's also grass, also crops, also shrubs. So you can see there's even more equal distribution. You can see there 14, 32, and 9% of spectral distribution. Well, this would also be a percentage because they're all converted into between 0 and 5. That's what the 255 is about. Converting the numbers into percentages, or to between 0 and 1, which is percent. Okay, so you can actually go and estimate or go and have a look at what is the probability distribution of each location in terms of these classes of land cover for your specific location within your region of interest. Remember, all this is based on our Sentinel 2 image for that period, and then it, as I said, generating its ID, then it matches that ID with associated classification in Dynamic World, and then we generate the elevation based on the probability distribution. Just have a look at it. You can see if I look at the image two-dimensionally, you can see there's quite a big difference. Let's just quickly wait for it to load. You can see it looks very different. You can see it looks much more visually appealing with the height of this being the probability distribution. The height being the probability distribution. Okay. So this is what the Dynamic World is, data set or methodology is all about. It's creating a 3D land cover image for your region of interest based on Sentinel and the algorithm that calculates the probability distribution based on those classes. Okay, remember to save. So that is Dynamic World. Now that's just, you know, this is just the intro video tutorial. Okay, there we can export it. Okay, so we can export this image to our folder. Okay, it shouldn't be there. To our project folder within our drive, within our Google Drive. I've called it land cover, land use land cover 2015, based on my region of interest scale, maximum pixels, etc., which is standard exporting scripts. Okay, let's save it again. So now your imagination should already be looking at, what can we do with this? You know, what else can we do rather than just creating a land use land cover image? And I said there's lots we can do, because first of all we sit with the time series, so we can see how this has changed over time, etc., etc. So there's lots more that we're going to do. This is just the beginning, but yeah, it's important that you understand the methodology or the thinking behind the code or the script, and how we get to this image. What are we doing to generate this image? Okay, so yeah, this foundation will be the basis of our next set of video tutorials using Dynamic World. As I said, it's a very interesting, very useful data set. Okay, and I think it will add value to your specific work or your specific analysis, or for your region of interest. Okay, well, yeah, thank you for joining me on this journey. First day of 2024. It's going to be an interesting journey that will see us right through to 31 December 2024. I'll be with you all the way, and yeah, please remember to like and subscribe and to share the video, and let's make it a fruitful year, and I'll see you on the other side.